All right, well, let's just reassess where we're at. This is the last week of classes. Brings a tear to my eye that we're not going to be talking about hydrology forever, but I guess all good things must come to an end. So your final design project is due 11:59 on Friday, and then the final exam is a week after that. And I'll talk more about the parameters of the exam in class on Wednesday. So today we're going to continue talking about stormwater detention. Remember, last Friday we spent some time discussing best management practices, ways to try and limit the amount of stormwater that gets generated. But what we're going to do today is, if it's unavoidable and if there's stormwater that has to be retained, then this will walk us through two different commonly used criteria for sizing ponds. So reminder that this afternoon at 5 there's the first meeting of the American Society of Engineering Management. So 5 o'clock, 12:01, and they're going to have pizza and fresh refreshments for that. So I'd encourage you to attend. All right. Just as a reminder, urbanization increases the speed at which water can run over the surface, because smooth surfaces like roofs and pavement allow water to move with a higher velocity than it does when it's flowing over vegetated land, and especially if there's like a heavy like forest litter of leaves and decaying trees and twigs and so on. Water really moves slowly on the forest floor compared to a curb and gutter. So it moves more quickly, which brings the peak flows sooner than they'd otherwise arrive at a certain location. But then they also increase the total volume of water that has to be retained. And so the purpose of stormwater ponds is to try and make the post-development runoff hydrograph look a little bit more like the pre-development runoff hydrograph. And at the early days of the pandemic, you may recur that people were talking about flattening the curve, which was the idea that in the COVID pandemic, that if people didn't wear masks, that we'd all get sick at the same time and it would overwhelm the healthcare facilities, compared to if we did mask and reduce the speed of transmission, then eventually everybody probably would get COVID, but it would be better for the system if we didn't all get sick at the same time. And so there's an analogy there that is very similar to the idea of stormwater detention, is that even if the same volume of water is being received by the pond or the stream, just delaying its arrival, and so that all of the contributing areas in a watershed aren't contributing flow at once, it's advantageous, and it's not going to overwhelm the infrastructure in the same way that it won't overwhelm the healthcare infrastructure if people get sick over time rather than all at once. So it's kind of an interesting analogy. When I started seeing figures like this online at early days of the pandemic, very naturally I understood what they're talking about with flattening the curve, because it's similar to a lot of things that we do in environmental engineering and hydrology. Okay, so let's consider, what if there was an area that was being developed, and this is a mixed-use commercial area that has some grassy areas, some roof area that's going to be completely impervious, and parking areas that are impervious. But in total, it's a 5-acre site, and the weighted composite C value after development is 0.70. And we're going to be sizing not only how big the pond needs to be, but also what is the required diameter of the outflow pipe in order to limit the flow to some specified flow rate. And also we want to make sure that the pond doesn't get too deep, because if ponds get too deep, then a variety of troubling things can happen. Like if a pond is really deep and it's meant to be a wet pond that always has water in it, then the wind that causes the water to circulate in the pond doesn't actually penetrate down to the bottom, and it can have layers of water that get very little oxygen at the bottom of the pond. And so that can be bad from the standpoint of breaking down biological materials, and the anoxic bacteria that do break down biological materials at the bottom of a pond in the absence of oxygen, they'll also convert inorganic material like sulfur to forms that are malodorous and unpleasant. And so that's one of the reasons we don't want ponds to get too deep, is that the wind doesn't stir it and mix it like otherwise it would. Another problem is that if the water's really deep, then it can be a drowning hazard if it's not got a fence around it, because ponds are often in like parks, areas that children are accustomed to going to. If it's a multi-use pond where it's a park and also stormwater detention when it's really wet, then suddenly you've got the risk of children in the vicinity of water that's not fenced off. So let's just say that for a variety of reasons, we don't want the pond depth to be more than 6 feet. I guess another reason could be that if you've got a berm or a dam around the edge to create that pond, then the taller the water gets, the higher the risk is of geotechnical failure of the soil, and then you could have flooding if the pond does fail. So we want to limit the depth to 6 feet, and then the outflow limit in some locations, the municipal regulations say that you are limited to 0.1 CFS of runoff per acre. And this is an outflow limit that I think is pretty common in West Virginia. There are a lot of municipalities, and it may even be a statewide thing, where they encourage new developments to limit their outflow to 0.1 CFS per acre of area that's developed. The other way we're going to look at it, because there's 2 tabs on the template file that I sent you, on the second tab we're going to look at what it would mean to retain the first inch of precipitation. And that's another guideline that you sometimes see in stormwater language, is just that they want you to provide enough on-site detention capacity so that when it rains, the first inch of water can be totally retained, and then any additional flow can enter the collection network and can run off the site. But the first inch has to be retained. And I think this second criteria is the standard that was applied when they built the new football practice facility on 3rd Avenue. They had to have a bunch of underground stormwater detention in order to receive all the water that comes off the roof of that practice facility, and they had to put enough volume there so that 1 inch of rainfall depth over the area of the roof, there had to be that much volume underground for the stormwater to be stored and released very, very slowly into the storm sewer. So here's our inflow hydrograph. Let's just say that that's a given. In reality, you generate this as well. And how would you generate the inflow hydrograph? Well, you'd maybe put together a watershed model, just like something such as WMS can give you a runoff hydrograph. For urban areas, we don't use WMS as much in urban areas. You can, but it really shines in rural areas. It requires a lot more manual interaction with the software to try and guide the flow along curbs and gutters, and so it's a great tool, but it's quickest at doing things for rural areas. But there's a variety of ways that you could come up with an inflow hydrograph if you know what the design storm looks like, and you know the time of concentration, and you know Q equals CIA, then you can generate an inflow hydrograph. But let's open up that template file, and together we're going to go through these 2 different criteria and see how big should the pond be, and what's the diameter of the outlet that we should design. We'll just assume it's a circular outlet, a circular pipe, a circular orifice on the end of the pipe, and we want to know what are we going to have to do to limit the outflow to 0.1 CFS per acre, and then also how big should the pond be in order to limit the depth to 6 feet. And we're going to use the same kind of simplifying assumption that we applied in Friday's example, which is just that the side of the pond is vertical, because it becomes a little bit more complex if we have an increasing surface area as the water depth increases. And you know, we could deal with that, but this is, for the size of the pond that we're going to end up getting, the difference is negligible for the area of pond. So I've already put in the inflow hydrograph, and we're going to step through all of the process here. Let's just say we don't yet know the size of the pond, but let's have it be 50 feet by 100 feet. And we'll just see what that gets us, if it's 50 by 100. And of course, area of the pond is going to be its width by, hold on, did the problem, it never said that the pond had to be square, right? So it can be any dimensions we want. Sometimes the shape of the pond has to follow some, you know, like the width is the same as the length, or maybe the length is double the width. Let's make it that way. I've already done 50 and 100, but let's set it up as a the width times 2. So now it's going to be twice as long as it is wide. Okay, so the area is width times length. The advantage of doing it that way is that when we want our pond to be bigger, we'll just increase the width, and then the length will also increase when we adjust the width. So we'll only have to be, like when we set things up and then we're looking to do the optimization, we'll only have to change one parameter for the pond area and then one other parameter for the pipe details. Okay, coefficient of discharge was given in the problem statement to be 0.6, and that's just, you know, part of using the orifice equation for our outlet. Square root of 2gh gives you the velocity, multiplied by the area of the pond gives you a flow rate, and then 0.6 accounts for the energy loss as the water enters the pipe. So 0.6 is the coefficient of discharge, and the diameter, we don't yet know how big the pond is going to be in terms of diameter. Here it's quoted in terms of feet. Let's say, what if it is a 6-inch diameter pipe? Then that would be 0.5 feet. Okay, so then the pipe area is pi times d squared divided by 4. So yellow are the parameters we're going to play around with once we've got the analysis of the pond set up, and we're looking to see how does the depth compare to the limit of 6 feet, and how does the outflow compare to the limit of 0.5. Why 0.5? Because in this first criteria, we're limited to 0.1 CFS per acre that's developed. And this is a 5-acre site. So that means we want to limit the outflow to 0.5 CFS. Okay, so let's go through and calculate each of these columns here. The first thing, volume in during the increment. If this is the inflow in cubic feet per second, and we can see that this is in 1-hour time steps, that means each row represents 3,600 seconds. So the volume in would be the flow rate multiplied by 3,600. So that tells us the volume that's in. The accumulated volume for the first 2 rows is just going to be the volume in. But then once we start having flow out, we're also going to account for the previous accumulated volume, the volume in, and the volume out. So at time 0, there's no accumulated volume. It's just, you know, the pond is empty at time 0. So you can just put in 0 for that. The water level is at 0 when we begin. The depth of the centroid, 0. Outflow from the pond is 0. The volume out is 0. Okay, so things get a little bit more interesting at time 1. The volume in will be this 1.8. Oh, did I? 1.8 cubic feet per second times 3,600. Okay, so during an hour, there's 6,480 cubic feet of water that comes into the pond. So the volume that's accumulated is the previous volume, which was 0, plus the new stuff that came in. But we haven't yet got any flow out. So the accumulated volume is just what was there in the previous step plus what came in. We'll have a different formula for the next row down. Okay, the depth would be the volume that's in the pond divided by the area of the pond. So the area of the pond right now, we just started off with it being 50 feet wide and 100 feet long. So it is that volume of 6480 divided by the pond area, which means the the water level right now is 1.3 feet, basically. And remember, H is defined as if we have a pond where the water's coming out and we're applying the orifice equation to tell us the velocity of flow that's exiting the pipe, then H is the depth of the water minus 1/2 the pipe diameter. Okay, so it's the water depth minus the diameter of the pipe. Anchor that reference because we're going to be always wanting to look up there as we drag that cell down. Pipe diameter divided by 2. Okay, and now outflow, Q out, is the coefficient of discharge multiplied by the area of the pipe, not the area of the pond, the area of the pipe, multiplied by square root of 2GH. So it is the coefficient of discharge, be sure to anchor the reference up there, multiplied by the pipe area, anchor that reference, multiplied by square root of 2 times 32.2 times H. Now since the formula is centered, I can't click on F14, but I'll just type that in. Okay. So that's the flow rate out through the pond. And in 3,600 seconds, if that's the flow rate out, then that would equate to a volume out of 3,480. Okay. So now we only have to make one more change and then we'll be able to drag everything down through the whole sequence of time and then see how our pond is performing. So drag down the volume in, because that's still just the flow rate in multiplied by the 3,600 second time increment. But now what's going to be different is the accumulated volume. Okay, so the accumulated volume is the previous accumulated volume plus how much comes in during this hour minus what came out during the previous hour. Okay? And I think all the rest of these cells, we can just drag down the previous formula for it, and we'll be okay. No, looks like I didn't anchor something. What is it? Oh, the pond area. Okay. Let's see, what else did I forget? Probably just that pond area. Yeah, all right. So let me try dragging it down again. Okay, so let's just make sure that it's reasonable. Like, if the pond depth is increasing, that implies that the flow into the pond was more than the flow out. So is that what we see? Like at hour 2, the water depth went from basically 1.3 feet and now it's at 3.2 feet. So the volume in was 12,960. The volume out in the previous hour was just 3,480. So yeah, more came in than went out, and therefore we'd expect that the water depth increased for the pond. Okay, so now we can just drag all of it down through the whole sequence of times that we're interested to analyze. Let's look at it over the course of 36 hours. So drag it down across all 36 hours. And, you know, the flow in stops, but we just want to see how long is it taking for the pond to drain, how quickly is it emptying. So anytime it says number, number, number like that, it means that the pond is now empty. So our limit for the depth was 6 feet. Let's see equals max, and then go down across the range, and that'll tell you what's the maximum water depth. It seems like it doesn't know how to interpret that number thing here, so let me just go up to where we have actual numbers. The pond got too deep. It's 15 feet deep. So does anybody know what we have to do to make it so it doesn't get so deep? We could change the pipe diameter, but, well, let's check to see which of the two. We can basically pull on two levers. We can pull on the area of the pond lever, or we can pull on the lever of the pipe area, meaning the pipe diameter. So the water's too deep. Now what about the outflow? Let's do the max and then across the range of values here, and it'll report to us what's the maximum outflow that we've observed. The limit was 0.5 CFS, and we're actually seeing 3.7 CFS. So this pond is wildly deficient. It's not good. The water's too deep, and the flow out of the pond is too high. So what if we made the pond a little bit bigger? Let's see in this analysis how does the maximum flow depth change if we, instead of 50 by 50, what if we made it 75? So that's going to be 75 by 150. Okay, the depth situation improved a lot, right? It went from 15 feet, now it's only down to 8.6. And the flow rate situation also improved, because if the water's not so deep, then there's not as much pressure pushing water out of the orifice at a high velocity. So ultimately we're going to have to play around with the diameter of the pipe a little bit for us to truly address the flow rate situation. But even bringing the depth of water down did help us on the depth, although it had the biggest effect on the flow depth, and it helped a little bit on the flow rate. Okay, so let's just see this max range. Probably we need to expand it, because before it was set to only include values that were positive and not these number ones here, but let me just expand that range down, even though those values we can see are smaller than the actual maximum amount. Same thing with the outflow. Let's make sure that our max range is actually taking in all the data that potentially could be the maximum value. It is, but we'll be a little more complete. Okay, so we can do a goal seek. That's maybe the fastest way to do things instead of, bringing it up by 5-foot increments, 80, 85, 90. Let's do a goal seek where we want to change the pond width. That will be the thing that it has control over. And the goal is for this cell, E11, to be 6. Okay, so data, what if analysis, goal seek, set this cell E11 to a value of 6 by changing the pond width. And this will get us really close to our final design. We'll still need to change things again after we optimize the pipe diameter, but let's just go for it. All right, so 94.95 feet wide and 189.91 feet long. That's the optimal pipe, or the optimal pond size if we have this 6-inch pipe diameter. But we can't go with the 6-inch pipe diameter because it's letting too much water out. So that's the other thing we're going to have to optimize. Let's do another goal seek on the pipe diameter. But then keep in mind, if we make the pipe diameter smaller, then water's going to be flowing out of the pond at a lower rate, and that's going to bring the water depth back up again. So once we optimize the pipe diameter, then we're going to be violating the depth criteria. So we'll have to go back and forth maybe a couple of times. So let's do that. Let's do a goal seek, what if analysis, goal seek on the maximum outflow should be a value of 0.5, and it can change pipe diameter. Okay, so okay. So that, instead of the, we were at 0.5 feet before for the area, the diameter of the orifice. We knocked it back quite a lot. Now it's 0.21 feet. And see, as I predicted, now our water depth is too high. So now we've got to make the pond bigger again. So let's do that. Let's, what if analysis, goal seek this to 6 by changing the pond width. We'll let it go. All right, now we're really good. Okay, so we're at our depth limit. We're below our outflow limit. We've got kind of a strange pipe diameter. They don't actually make pipes that are 0.214 feet in diameter. But what we could do is we could get a quarter foot would be 3 inches, right? 3-inch pipe. So 3-inch pipe out. So that's 0.25 foot diameter. And then you just put like a small ring around, like a plate. You could have a metal plate on the front of it that has a slightly smaller diameter. And so you could just machine that to the size that's needed. Now 112.91, maybe just to make it easier on the contractor, we could say 113 feet. But that's our design. So we meet the criteria. So if our municipality says we're limited to 0.1 CFS per acre of area that's developed and a pond depth of 6 feet, we meet both of those requirements. And we're not going to save, there's really no more meaningful optimization that we can do. I mean, you'd try to want to get the outflow to maybe be a little bit higher, but if we do, then we'd have the pond getting deeper again. So we'd need to make the pond a little bit bigger. So probably the real savings are in minimizing the size of the pond, not minimizing the size of the pipe. Any questions on that process? Okay. So now let's do the setup for part B, and then I'm going to have you work independently on like the pond analysis and optimization part. There are a few things that are a little bit different here when it says we want to retain the first inch of precipitation. So if we're retaining the first inch of precipitation, we have to apply the rational method to find out the volume of water that's going to be stored without outflow. Let's do the same thing where, you know, we have a pond that's 50 to start with, and then the length is the width times 2. Okay, so we've got some placeholder pond area. Coefficient of discharge, again, is going to be 0.6. Let's have a placeholder pipe diameter. Again, we'll maybe try 0.25. Okay, area of the pipe will be pi times d squared divided by 4. Okay. So the rational method now. The C value for this development is 0.7. That's the composite C value. That's going to apply to 0.7 to Q equals CIA. And it says that the first inch of precipitation has to be retained. So the depth of precipitation we're talking about in feet is 1/12 of a foot. So the precipitation depth that we're going to base this all on is 0.08333 feet. Okay, the area of the development, this is a 5-acre development. 5 acres times 43,560 square feet per acre. So the development area is 5 acres times 43,560. So the total number of square feet of this development is 217,800 square feet. So the volume of water that has to be stored is going to be the C value multiplied by the precipitation depth multiplied by the development area. So when it rains, the first inch of rainfall has to be retained, and of the first inch that falls, some of it is just like due to surface wetting or infiltration. We don't have to retain that part. It's naturally retained. So our artificial retention has to be for 70% of that first inch of rainfall. So that's why we applied the C value to this volume calculation. That's the component that we're going to engineer the storage for. 70% of that precipitation volume. Okay, now this part, height of the pipe center line above the pond bottom. The criteria, if you look at the handout I gave you, it goes into a little bit more detail than this slide, but it says that we're not talking about temporary detention, we're talking about retention. That first inch of precipitation is going to be in the pond and not flowing out. Like, you have to have an inch of rainfall and then water can start coming out of the pond. So look at this drawing I have on the whiteboard. What that means is, like the way it's drawn right now, as soon as the water level starts rising, it's going to flow out of the pipe. But if we raised the pipe above the bottom of the pond, and we had a certain volume of dead storage, like this, so now the water level has to get up to a certain point before the water was going to flow out. So we have to lift the pipe off the bottom of the pond to truly retain the first inch of precipitation. So how high off the bottom? We don't know yet. Let's just say, is it 1 foot? All right. So we've got 11 minutes. We've got the inflow. I'm going to pause, and you go through the same steps that we did before in analyzing this pond. And for now, don't worry about the height of the pipe center line above the pond bottom. We'll look at that in a minute. We'll make adjustments, but just go through in the same way that we did on tab A. Here for tab B, set it up, and then once you've got the first couple of hours, then we'll take a look at it together. Okay. If you're not yet up to this point, you can keep working, but I just wanted to kind of take a moment so we can analyze whether we're meeting this requirement that the first inch of precipitation has to be retained. So the first inch it means that we have to retain 12,700 cubic feet of water. So that means the pond has to have 12,700 cubic feet of water in it before it can start discharging. And if we see, it starts discharging here, and it's only got 6,000 cubic feet of water in it. So we're going to have to lift the bottom of the pipe higher off the bottom of the pond. And what that's going to do is it's going to make it a little bit tricky for us to calculate H. Right? The depth of the centroid isn't just going to be the water depth minus half the diameter. So like if we lift the pond, if we lift the, well, by the way, if this is a pond area of 5,000 feet and we need to have 12,000, then that would imply that, you know, we need to have a depth of water that is over 2 feet before the water starts flowing out. So we need to have like 2 feet here. But what we knew from the prior one was that, you know, we're obviously going to make this pond bigger. So what I did when I was solving this in the past was I set up like an if statement that was like if the water depth is greater than the height of the center line above the pond bottom, then the depth of the centroid is just the water depth minus half the pipe diameter. Otherwise, it's 0, because the outflow from the pond is going to be 0 until we have some positive depth. So we don't have to have an if statement. You can just kind of manually control that. But let's say we're going to take the centroid up 2 feet. So we want to have 2 feet, or the center line. So if we have 2 feet of depth from the bottom of the pond to the bottom of the pipe, and then the pipe diameter is 0.25, then that's 0.25, then that would be 2.125. So 2.125. Okay, so then that's going to make the depth to the H is going to be 0 until the water depth becomes more than 2.125. So now it is. Now you can see the depth is 3.888. So now H is that minus this value. So that is going to change our outflow. So we see, you know, how much storage volume is there before flow starts going out? Well, we start to see a little bit of flow out now that it's up to 19,440. So we can feel pretty good about the fact that we do have that dead storage down at the bottom. So now the rest of the analysis would be that same thing as before, where what we did was we looked to see what's the maximum value of the water depth. And here it's getting pretty high because that pond's not big enough. And then what's the maximum outflow? And we want to make sure that we have a situation that limits it to 0.5. So we need to make our pond bigger than it is right now because the water is getting too deep. So 100 by 200. That's maybe too big. Let's see, why is it going to 0 here? It's because the depth of the centroid thing. We have to manually know that if the water depth is less than 2.13, then there's not going to be any flow out. So we have to manually override that and say that the flow is 0. The flow is 0. There's no flow out. But then as long as finally when the water depth is more than 2.13, then we will start to have flow out. Okay, so 100 by 200 gets the depth to 7.6. So we could go through goal seek, or we could just manually play around with the sizes until we find out what is the size of the pond that's going to allow us to have that maximum depth, and then check to see how the flow rate is doing as well. So for this one, it looks like 114 by 228 would do it. The pipe diameter of 3 inches is going to limit the flow out. And then we've got a certain amount of dead space at the bottom of the reservoir, at the bottom of the pond, that meets the criteria that was set. Okay, 150, we're out of time. Remember that meeting at 5 today, down the hall, free pizza, and then your storm sewer sizing. I cut off half of those inlets. I gave you the revised handout, and it's also posted on Blackboard, so still haven't heard anything from Bentley on getting more inlets. So unfortunately, you'll only have 5 inlets in your storm sewer design, and then the pond stuff, I think you should be in a good shape to do that now as well. See you Wednesday.